In this video, we're going to learn how to use congruent triangles to help us find the information we're asked to discover. So let's start with this example. It's asking us to list all pairs of sides and angles that are congruent based on what's already been given. And obviously we can see that there are two right angles, and we like right angles because they often make our computation or observation a lot easier. So angle TUA is congruent with angle VUA, and also we're given angle TAU is congruent with angle VAU right there. And the third thing we know is UA segment is congruent to itself. And because of that, notice that we now have an ASA situation. We have an angle sandwiching a side in between. So because we have, by ASA, we can draw the conclusion that the two triangles, TUA, is congruent to triangle VUA. These two triangles are congruent. Here's a reminder of what's the definition of congruent figures. Remember that the most important thing is that congruent figures have to have exactly the same size as well as the same shape. Meaning, if I have a triangle, its congruent triangle has to be a triangle. It can't be a square or a rectangular. And if I have congruent triangles, their angle measures have to be congruent and their length have to be congruent, and that's what it means by same size. And going back to our previous diagram, it's asking us to list all the other angles that are congruent and the sides that are congruent that we have not talked about. So by observation, you will be able to tell that T and V, the two angles, are congruent. TU is congruent to UV, and TA is congruent to VA. And that covers all three sides and all three angles. So to summarize, we have just talked about CPCTC. It's not just a tongue twister that geometry teachers like to use every now and then to make us sound smarter than we are, but rather it stands for corresponding parts of congruent triangles are congruent. Again, it stands for corresponding parts of congruent triangles are congruent. And the abbreviation comes from the first letter of each word in this sentence. Again, what it means is that if two triangles are congruent, its corresponding sides and angles have to be congruent. And in order to use this in a proof, you first must prove that the triangles are congruent. Right? Once you prove the triangles are congruent, you can use CPCTC to prove that all other sides and angles are congruent. Let's look at this example. It's asking us to list all pairs of sides known or given sides and angles already, and we know that MQ and NT, that's given, they're congruent. We also know MT is congruent to itself, and then because these two lines are parallel to each other right there, because they're parallel to each other, so angle QMT is congruent to angle MTN. And now we just created, look at that, two sides sandwiching an angle in between. So we have SAS situation. By SAS, we have two congruent triangles, NTM and QMT. And if I have to list all the other pairs, it's all the pairs that hasn't been mentioned. Angle N and angle Q are congruent. Angle NMT is congruent to angle QTM. And segment MN is congruent to segment TQ. So that's a summary of the process of using CP/CTC. Now let's look at how we use them in proofs. It actually, if anything, this is making proof a lot easier. We're given that MP bisects angle MNQ. I'm sorry, that's an O. So in other words, these two angles are congruent to each other. That's given. And I can draw the conclusion that MNP is congruent to O and P. And that's because of the definition of a bisector. It cuts that angle in half. And I also know that MN and NO are congruent, and that's given. Notice at this point I already have an angle, I already have one of the sides, and I happen to notice that if I have MP, I would have two lines sandwiching an angle. So MP obviously is congruent to itself, and that's by reflexive property of congruence. And now I have my third S here, right? So by by second S, by SAS, I now have enough evidence to draw the conclusion that triangle MMP is congruent to triangle ONP. And because of that, the corresponding sides, MP is congruent to PO, and that's CP/CTC. Let's look at this example. We know CG and ZG, that's given. These two are congruent. That's great. I have one side already, so I have my first side here. And I also know that M is midpoint of CZ. That's also given, and because of that, I have CM, that's an M, is congruent to ZM, and that's definition of midpoint. And so now I have my second line, that's my second S right there. And finally, if I just get my third side, which is AMG, and happens to be congruent to itself, and that's reflective property of congruence. So now I got my third S. So by SSS, I have two congruent triangles. CMG is congruent to triangle ZMG. And by CP/CTC, I know that when the triangles are congruent, the corresponding angles C and Z must be congruent to each other. See, that's how we use CP/CTC. We first have to prove the triangles are congruent, and then by extension, using CP/CTC, we can conclude about the other information. Okay, in this example, DB is congruent to CB. And that's given. We have one side already. And the next information is about the two lines that are parallel. But before I get there, I'd like to get the whatever is the obvious. So angle ABC is congruent with angle, angle ABD is congruent with angle EBC. And that's because they are vertical angles. And by vertical angle theorem, they are congruent to each other. So now I have one side, I have one angle, and hopefully I can capture another angle or another side. Now I can use, I don't have anything directly given to me about angles and sides other than these pair of parallel lines. And because they're parallel, you notice that angle C and angle D are congruent. So here's my second angle. Now I've got two angles and a side, and it's an ASA situation. So actually I should write this. This is because it's alternate interior angles theorem. And then now I can conclude by ASA, the two triangles are congruent, ABD and EBC are congruent, and therefore AD is congruent to EC, and that's by CP/CTC. Okay, so that's a quick example. Here's another one. It is given that YX is congruent with WX, so YX and WX are congruent. I've got one line already, and because ZX is bisects the angle YXW, so both of these are given, and now I can conclude that angle YXZ is congruent to WXYZ, and that's the definition of bisector. Don't learn your teacher's bad habit. Write out everything, every word, definition of bisector, okay? And now we can say, we also know XZ is congruent to XZ, and that's reflexive property of congruence. And because of that, notice that we now have a situation that's SAS. We have the angle sandwiched in between by two sides. So triangle YXZ is congruent to triangle WXZ. And by CP/CTC, we conclude the corresponding sides, WZ and YZ, are congruent. Okay? So here's another example that's slightly more complicated. It's given us some limited information, and it's asking us to prove whether O is the midpoint of SR. In other words, and see if these two sides are congruent or not. And in order to prove that, we have to prove the two triangles are congruent, and hopefully we can use CP/CTC. Okay, it is a tongue twister, isn't it? So let's start. It says that first of all, O is a midpoint of NP. So let's write that down. O is midpoint of NP. And that's given, and therefore we can easily draw the conclusion that ON is congruent to OP. They're of the same length, and that's definition of midpoint. And then secondly, we also know that these two angles must be congruent, so angle NOS must be congruent to angle POR, and that's because they're vertical angles, and by vertical angles congruence theorem, they must be congruent. That's all I can see right now, but thank goodness that what's also given is here. Angle N and angle P are congruent, and that's given again. So again, now we have, I think we've got everything we need, because if these two angles are congruent, notice that we've got two angles sandwiching a side. So we have ASA situation. So by ASA, we can prove that triangles NOS is congruent to triangle POR. And by CP-CTC, we now can say OS and OR are congruent. If OS and OR are congruent, by definition, O is the midpoint of SR. And that's by definition of midpoint. Okay? In this example, we're given DA and YB are congruent, and then there are two right angles right here, and we're asked to prove whether this angle D and this angle B, are they congruent to each other. So let's see how do we address this issue. We like the fact that we're already given that one pair of corresponding sides are congruent. So one thing is done. And then the next thing that's given is that the two angles, BYA and DAY, are right angles. And that's given. And then, therefore, we can conclude that angle DAY is congruent to angle BYA. And that's right angle congruence theorem, if you recall that one. So now we've got a side and an angle. And obviously, AY is congruent to AY itself. And that's reflexive property of congruence. So now we've got two sides and an angle, and with the angle being sandwiched in between. So in other words, we have a SAS situation. So my DAY, triangle DAY and triangle BYA are congruent. If the two triangles are congruent, by CP-CTC, the corresponding angles D and corresponding angle B are congruent with each other. Okay, I hope this is helpful. See you guys in class.